Have you ever wondered how microscopic things move? They definitely don't have legs. Certain organelles such as cilia, which are the hair-like structures, and the long tail-like structures called the flagella help the little ones move. But how do these things work? What's the physics behind it? The answer lies at a low Reynolds number. All microorganisms live under low Reynolds number conditions, but what does that signify? Reynolds number is a unitless quantity that helps us tell if the flow is laminar or turbulent. The higher the value of Reynolds number, the more turbulent is the flow. Mathematically, the Reynolds number is a ratio between inertial and viscous forces. Where ρ is the density of the fluid, v is the fluid velocity, L the length of the column, and μ is the viscosity of the fluid. Viscous forces here are like frictional forces which keep the layers of fluid together, hence more the viscous forces, the flow will be laminar, but once inertial forces are large enough, the layers misbehave, and we have the turbulent flow. Now how is this all relevant to this little fella? Before we dwell on it, let's watch this video to see why understanding laminar flow is important to understand the movement of the microorganism. In the video, we inject different ink colors at different positions in the given solution. Now when we start mixing the solution, you can see the droplets seem to have dispersed in a fluid. But to one's surprise, when we retrace our steps, we practically unmix the droplets. This happens because in a laminar flow the layers of fluid don't intermix or cut each other, they get twisted and stretched, but because the frictional forces between the layers haven't let go, they can be untwisted and unstretched like some gelatinous substance. Now, what does this reversibility means for organisms? To see that, let's take the example of a scallop. A scallop thrusts itself forward by clapping its shells against each other. In a way the movement is not cyclic, it retraces its steps. This works in a high Reynolds number situation because inertial forces dominate. But, in a low Reynolds number environment, it will never be able to move ahead. So we need movement patterns such that they don't retrace steps. Now, we know these microorganisms exist and move, so we must be able to construct some such patterns, right? Consider the simplest one, a unibody, represented by a single line. Even though it does not retraces its steps, it is still unable to move ahead as it keeps pushing the upper layers backward and lower layers forward. Next, let's try an organism with two segments. If we move them both in the same direction, we'll simply reiterate the first case. Let's move them in opposite directions. As the body parts are in the same plane and can't go over each other, they will have to retrace the steps and hence come back to the same position. What if we move just one of the arms? Well, clearly that doesn't work either. Next, let's take three. Next, let's take three segments. Hope this one works. It has four different configurations circling back to the first one without retracing its steps. It does. Apart from these, other constructions that do work are these. This one consists of just two balls rolling onto each other. This next one is a flexible oar-like structure. It doesn't retrace its steps as the returning configuration is different and thus pushes the organism ahead. Then there's also this corkscrew configuration. It rotates either clockwise or anti-clockwise and thrusts itself forward. There could be many more. One can try and construct as many as they could. This video is based on the paper Life at Low Reynolds number by EM Purcell. You can read further and find more interesting constructions and their implications. Thank you for watching.